Hello, welcome to the next lectures, which will be about the gas chromatography. In the last lecture series, we looked at chromatographic analysis as such, and in this lecture, we are going to focus one of the two most important chromatographic techniques, namely the gas chromatography. In the next lecture, so the last lecture about the chromatographic methods, we are going to look at liquid chromatography. In the gas chromatography lecture, a lot of this is based on a legendary book by Harold McNair, Basic Gas Chromatography. So many figures come from this in this book. So if you are more interested in gas chromatography, I definitely recommend you to have a look at this book to read more intensively about the gas chromatography techniques. Gas chromatography, as the name suggests, is a chromatographic method where we use mobile phase as a gas as a mobile phase. The stationary phase in gas chromatography can either be a liquid or a solid, and increasingly, this is actually a liquid phase nowadays used as the stationary phase. And the analytes that we are determining with gas chromatography are mostly organic compounds and volatile organic compounds. However, also analysis of inorganic gases, for example, is possible. But the big part of the samples are analysis of organic compounds, volatile organic compounds. So why is gas chromatography such an important method? Firstly, gas chromatography was actually the first of the two common chromatography methods that was automated to the level that there was widely available commercial instrumentation. So even though the first experiments that Michael Sweat carried out were actually liquid chromatography separation of the pigments, liquid chromatography became commercially widely available only later than gas chromatography. So gas chromatography was already very popular in the 60s and 70s, while liquid chromatography picked up pace after gas chromatography. So gas chromatography historically is a very efficient method of separating compounds, and it has numerous wide applications. Therefore, it can separate very many compounds simultaneously. It is very efficient, meaning that the theoretical plate numbers that can be achieved with gas chromatography are very high. So the plate numbers are somewhere around 100,000 theoretical plates per analysis per compound. So this is very high, and it's still much higher than is achievable in the liquid chromatography. Though the number of compounds that can be determined simultaneously today is also similar for liquid chromatography, especially after coupling with mass spectrometry. But historically, gas chromatography is more efficient and able to determine and separate many more compounds. So this is easily in the range of hundreds of compounds. Also, with a suitable detector, as many detectors are available for gas chromatography, the quantities of the compounds that can be determined are very low. So if a suitably sensitive detector for the analyte is chosen, then determination of the compounds in the ppb range is easily possible. But this strongly depends on the detector and on the compound that we are wanting to quantify. Also, with automation, with the possibility to automatically inject samples to the gas chromatography systems, hundreds of samples can be analyzed per day. So this also means it makes it suitable for wide-scale analysis of environmental or pharmaceutical samples or medical samples, anything at all actually. And it is also suitable for quantitative analysis, though usually internal standard methods need to be used to actually get nice quantitative results. However, there are also limitations. Gas chromatography, due to the fact that our mobile phase is a gas, which means that the compound needs to, in order to move with the mobile phase through the column, it needs to become volatile, it needs to vaporize to the gas phase. Therefore, the compounds that we can analyze have to be at least somewhat volatile. So that means that their boiling points can't be too high, which of course limits the scope of the method. For example, automatically we understand that two polar compounds which have very high boiling points can't be analyzed. For example, proteins are completely out of the scope for the gas chromatography analysis. And it's also not very nicely suited if any of the sample components are not thermally labeled. So because we use high temperatures in introducing the sample to the chromatographic system through the chromatographic process and also in detection. So if we have compounds that we are interested in and which are thermally labeled, then gas chromatography can be very problematic, or if not, absolutely not applicable. However, there can be ways to overcome these limitations. For example, one of them is derivatization, which is used to make compounds more volatile than they are. And this can be done then by carrying out chemical reactions with the analytes that are themselves originally not sufficiently volatile for the gas chromatographic analysis. To give you some grasp, how does a chromatogram from a gas chromatographic analysis look like? Here is a chromatogram of a peppermint oil that has been chromatographed with gas chromatography. And the aim here has been to see the full richness of the aromatic compounds and especially aroma compounds in the gas with the gas chromatographic analysis. And you can see that this specific chromatogram has been obtained by a chromatographic method of 45 minutes. And we have here actually very many peaks. From the aroma compounds, 29 have been labeled, but there are actually many more other compounds which are then not associated with the aroma. And you can also actually see from here how efficient gas chromatography is. The peaks are super narrow. It's maybe hard from here to evaluate how narrow exactly, but peaks in the second scale are completely normal in the gas chromatographic analysis. Going a bit in front of the topic, saying that in the normal HPLC, the peak widths are usually about half a minute or even longer, and in high performance or ultra high performance liquid chromatography, they could be in the scale of 10 seconds or something like that. So the gas chromatographic peaks can be extremely narrow compared to the liquid chromatographic peaks. And actually, it would be a good to think for a second, why are then gas chromatography peaks narrower? What are the processes when we think about the one diameter equation that are so much more efficient in the gas chromatography compared to the liquid chromatography? And we can come back to this in later discussions with you, but think about it. So the question now is, what are the basis of separation in the gas chromatography? How are the different compounds separated? So the separation, similarly to all other chromatographic methods, is, or almost all chromatographic methods, is based on the interactions between the stationary phase and the analyte, or then the mobile phase and the analyte. And In here, the interactions can occur between the analyte and the stationary phase, and those these interactions are largely driven by the volatility of the compounds. So compounds which are less volatile are stronger interacting with the stationary phase. However, stationary phase chemistry, so the polarity of the stationary phase, can add additional interactions to the separation mechanism. Traditionally, the stationary phases are not very polar, and therefore the interactions between the stationary phase and the analytes is driven by the volatility of the compounds. So the compounds which are more volatile are more of their time in the gas phase, so they are easily volatilized and they move faster through the column, while compounds which are less volatile are spending more time in the stationary phase and therefore move slower through the gas chromatography columns. And so a rule of thumb is that compounds which are more volatile are less interacting with the stationary phase. So how to practically carry out gas chromatography? And for this, we need an apparatus to carry out the chromatography. And everything starts with the mobile phase, with the carrier gas, which is directed into the chromatographic system. And very important part here is the flow control, which means that we have to keep the flow constant at all times of doing the chromatographic analysis. And this is extremely important to achieve reproducibility of our chromatographic systems. Also, we usually want to purify and dry the carrier gas to make our columns live longer and not to cause any unwanted reactions between our samples and gas and carrier gas, as well as the stationary phase in the column. We used to bring the sample to the column with an injector, which can be heated with a heater. And there is usually a possibility to split the flow after the injector, so that only part of the sample actually goes to the column and part of it can go to the waste. Then we also have a column here. The columns, which are to nowadays usually capillary columns, are very long, so that's why you have here this long column with very many turns. And the column is placed in a column oven, which is important to regulate the temperature of the separation. Because the compounds need to move from the stationary phase to the gas phase to move through the column, it's important that the vapor pressure of the compounds would be constant from one run to another, and therefore we need to keep the column temperature very precisely regulatable, and therefore we need to have a column oven where our column is placed and where our separation, chromatographic separation, is carried out. And finally, to register the compounds once they elute from our column, we have a detector. We can have here numerous different, and then we probably have here also a computer system that actually registers our chromatographic peaks. So the first important part is the mobile phase, and as this is gas, we also often call it the carrier gas. Its job is to carry the sample, the analyte, through the column. And at the same time, it should itself not really anyhow interact with the stationary phase. So it should be inert. And it should be also inert in the sense that it should not react with the sample and then also not with the stationary phase. So from the inertia point of view, nitrogen is a very good carrier gas, as well as helium. And rarely though, but historically, hydrogen has also been used as a carrier gas. Today, hydrogen is not very much used, even though it sometimes can be cheaper than helium, for example, in some countries, but it is a lot more dangerous to actually operate. So hydrogen is usually avoided if possible, and primarily nitrogen and helium are used. It is important that independent of the exact choice of the carrier gas, it is as pure as possible. And especially important is its freedom from oxidizing agents, so oxygen and water. And oxygen and water are very, very important to avoid any possible reactions between the carrier gas and the stationary phase. So if there are residues of oxygen, for example, it is possible that the carrier gas, or actually the oxygen in this carrier gas, would react with the stationary phase material, would oxidize it, and therefore the stationary phase would age and its chemical properties would change during this oxidation. So chromatography would not become any more reproducible, and the retention times that have been observed on one day would not reproduce to another day. And it's very likely that peaks start tailing because these oxidized stationary phases may have very different retention mechanisms than the original stationary phase. So to avoid this kind of problems with the stationary phase, it's very important to use as pure, as dry, and as oxygen-free carrier gas as possible. And usually a number of different purification columns are used before the carrier gases are directed to the real column, where then the water is absorbed by these purification columns, and also other residues should be removed. Also, for example, in the gas on top of the gas cylinders where the flow regulators are, it's very important that there wouldn't be too many alkanes used there in the oiling of the systems to cause any contamination of compounds that could also be detected with the detector. So freedom from these compounds is also very important. There is a special system in denoting the purity of the carrier gas, and it's usually denoted something like 5.0 or 4.0, and this 5 indicates the number of nines in the percentage of the purity, and then the 0 means that after how many nines comes the first 0. So if we say that the purity is 5.0, then this means that the purity is at least 99.999 percentage. 6.0 would be that the purity is better than 99 and then 4 nines percentage. The carrier gas also needs to be compatible with the detector. And for example, the limitation here is that for mass spectrometric detector, helium is needed and nitrogen is not suitable, because nitrogen itself is also ionizing in the mass spectrometry, and it causes high background therefore. It's also important to regulate the flow of the gas, that carrier gas, as precisely as possible. And this is because we usually use retention times for identification purposes. And this means that retention times need to be as reproducible as possible. But if the carrier gas flow changes by, let's say, 10%, then the retention times will also shift by about 10%. And if we chromatograph then our sample at one flow rate, but then the standard at another flow rate, where the flow rate was, let's say, 10% lower, then all retention times are roughly 10% longer, which means that then we would not be able to actually accurately identify which compounds belong to which peaks in our sample. So this reproducibility of the flow rate of the mobile phase is extremely important in gas chromatography. Now, the sample is injected to this carrier gas flow, and it is important that the sample is very rapidly brought to the gas phase so that it can be brought with as narrow band as possible from the injector to the column to keep the peaks as narrow as possible and to avoid any kind of peak broadening. So it has to happen very rapidly. And actually, two things have to happen very rapidly here. Firstly, the sample needs to be volatilized as rapidly as possible. And secondly, the sample needs to be carried to the column as rapidly as possible. And therefore, the injectors are systems which are usually heated to a high temperature. Usually the temperature is about 50 degrees higher than is the boiling point of the sample to bring as fast as possible all of the sample components to the gas phase and then rapidly direct them to the column. It is important that this is sufficiently high so that everything is vaporized, but it's also important that the sample would not decompose in the injection, during the injection. So this from here comes the limitation. If some of the compounds are being too temperature label, so that means that they would decompose at the injector temperature, while others maybe aren't even volatile yet. So this means that probably this kind of analysis is not suitable for the sample. So all of the compounds of interest have to be sufficiently temperature label so that we would be able to get all of them into the column so that they wouldn't decompose or anything. When we have liquid samples, then we usually inject a microliter, around 1 microliter, can be less, can be slightly more, especially when we use capillary columns. When we use packed columns, then these volumes can be even up to 10 microliters. And the injection is usually done manually with a micro syringe, where manually the analyst can take the amount of sample that is needed to be injected, or it can be done with an autosampler. And increasingly, the autosampler system is used. Autosamplers are, of course, more reproducible, the injection volumes, but it's also the advantage that analysis can be carried also out of working hours, which means that the samples can be run also overnight, which is, of course, a big advantage when we talk about large cohort analysis or just very many sample analysis that need to be carried out. It's also possible, of course, to analyze gases. And for this, gas-tight syringes, for example, can be used to take the sample. And gas injections are also possible both manually and with an autosampler. And for the injection systems, there are very many different actual modes. The most common ones are splitless, and on-column injection. And we will look more into the split injection, which is kind of a traditional way to analyze samples in the capillary column analysis. But before we get to this, just maybe a caution point here. Even though the liquids and gases both can be analyzed, in case of liquid samples, all of the compounds actually need to be volatile, which means that the boiling point needs to be sufficiently low. But what is especially problematic is when we have mixtures of gases and liquids. And one of these cases can be solved with something which is called a headspace analysis. So if the analytes that we are wanting to analyze are sufficiently volatile, then we can use the analysis from the gas phase, even though our sample itself might be a liquid. So schematically, it is represented here like this, that the sample consists of 3 different molecules, for example, but the analyte molecules, the orange dots here, are so volatile that if we put this sample, even though a liquid, into a vial, a closed cap vial, uh, then and wait for a sufficient time for the gas phase and the liquid phase to equilibrate. Then with some time, sufficient part of the analyte molecules actually goes to gas phase. And in this case, we could actually sample with a syringe these analyte molecules, the orange dots, from the gas phase, so that we would not even need to inject the rest of the compounds or the rest of the matrix um, from the liquid phase. And it can be, in this case, when the compounds of interest are sufficiently volatile, that we actually take a gas sample here from the headspace. So with headspace, we mean the gas phase that is on top of the liquid in a closed vial, or that we use an additional solid phase to collect the sample and then get it out from the um, vial. But the idea is that we still sample from the gas phase. And we will look at this headspace with a fiber actually also in the sample preparation lecture that is coming in the quite end of the course. But the main idea here is that if the compounds are volatile, then we can also make analysis just directly from the gas phase on top of the liquid phase. And this is, for example, one solution to analysis if our samples contain water. So generally water is at higher temperature, it is an oxidizing agent, and therefore our samples should be as dry as possible. So we can't inject water samples, which is kind of a problem because very many samples that we might be interested in can be in water or are naturally in water. So there are two possibilities here. We could either do a solvent exchange during our sample preparation. We could use a liquid-liquid extraction or solid phase extraction, and we will look into the mechanism in the sample preparation lecture later. Or we could, if our analyte is sufficiently volatile, we can try to use this kind of headspace analysis. The headspace analysis is, for example, very suitable if we have large water concentration samples and we want to determine, for example, ethanol or other similar small short chain organic molecules. For example, ethanol from blood can be done like that, or ethanol from the windshield liquid, and this can be done without changing the solvent. So sample preparation can be very, very minimal, just putting the sample into this vial and analyzing the gas phase from the top of the sample. However, other samples may need to be dissolved or diluted with a suitable organic solvent that itself also has a sufficiently low boiling point. So now about the injection with a split mode. So split mode is a very often used in the capillary gas chromatography. So cases where the columns are capillary columns. And the reason here is that when we inject our sample, we want to get the sample to the column as a very narrow band to not make already when injecting the peaks very broad. So this means that we should avoid very large volumes of gas to the entering to the column. And when we do the math with the ideal gas equation, then we see that the injection of 1 microliter of benzene would result in 600 microliters of gas, which means that that is quite a lot. And actually it would take tens of seconds to get such a volume of gas to the capillary column, and it would essentially overload the column, which means that our peak would become instantly broad just because the volume injected to the column would be too large. And we want to avoid this peak broadening due to the injection of a large volume. We can't really very much decrease the sample size that we inject. 1 microliter is about in the range where we can still somewhat reproducibly take the sample volume. So we can't narrow this down 100 times. It would be essentially impossible. So therefore, a smart solution called split injection has been uh, designed, and this is a injection type where we use a system where majority of the sample is not directed to the column. And let's see this here on the example of the injector here. So the sample is injected from here with a syringe. So the needle pierces first the septum, an inert septum that should not somehow cause any compounds to enter the column. It should be as inert as possible. And it also avoids the carrier gas to leave from the system in this direction. So it is only permeable with a syringe and with a syringe needle from this side. So the needle enters to this injector, and in here the important part is the glass liner, which is inert and should not react with the sample or should not be absorbing any analytes or anything like that. And this is heated. So with the syringe, the sample is carried in here. The injection is made by pushing down the plunger. The sample enters here, and on the surface of the glass liner, the sample is rapidly volatilized. The carrier gas is flowing through the injector and is carrying this rapidly vaporized sample downwards. And now there are two possible exits for the sample. One which leads to the capillary column, and another one which is called the split vent, or can be thought also as essentially a waistline. So the sample that is directed for analysis leads to the capillary column, but the rest is then directed to the waste essentially. And the split ratios that can be used are somewhere, the smallest can be somewhere to 1 to 10. So this means that one part goes to the column and 10 goes to the waste. But most usual are somewhere between 1 to 50 to 1 to 100. So about 1 to 2% of the sample actually goes to the capillary column. And this split injection is very important to keep the columns, the peaks in the column narrow, and therefore enables us to get high resolution. And it's also therefore suitable for analysis of fairly concentrated samples. So we don't overwhelm our column or overload our column. And also dirty samples can be analyzed because all this dirt is not reaching column. Majority of this is going to the waste. And in some cases, even if the glass liner additionally is filled with some kind of inert material such as glass wool, very dirty samples can be injected so that the glass wool is just absorbing the major part of the dirt, and then only the well vaporized part is actually injected to the column. But the problem is that when we are dealing with compounds which are really, really close to the detection limits, then we would not really want to waste a lot of our sample and direct it to the waste, but we would actually like to get it to the column and being detected after the column. And in these cases, splitless or on-column injections are very useful. There are also other techniques such as cold on column and others, which are also used for solving these additional problems. So split injection is kind of standard in the capillary column analysis, but for other samples there could be need for other injection modes as well. Now, when we have our sample vaporized and directed to the column, then we should also look at what is this column then, or which kind of columns we have in gas chromatography. And largely divided, we have capillary columns and we have packed columns. In case of capillary columns, the stationary phase is covered on the inner wall of a very narrow capillaries. So these capillaries are about something like 0.25 millimeters in the internal diameter, and the walls are then functionalized with the stationary phase, which is a liquid, and the interaction of the compound is of the analytes is then between the inert gas flowing in the tube and between the stationary phase on the walls of this capillaries. And kind of more traditional are packed columns, where round particles have been first functionalized with the stationary phase. So there is an inert particle here with the blue, dark blue color, and then the actual stationary phase that causes retention of the compound. So this liquid phase is covered on the as a layer on the stationary phase, and then the stationary phase is used to pack this column. So it's tightly packed with the particles that are carrying the stationary phase. So for the capillary columns, which are also called wall-coated open tubular columns, so COT columns, usually silica capillaries are used, which are sufficiently inert and temperature stable to be actually placeable to the column ovens and usable during the chromatographic processes. The good part of the capillary columns is that the resistance to the flow is low, which means that the columns can be made fairly long. Usual columns are somewhere between 15 meters to 30 meters, but also very long columns have been made. So somewhere like 100 meters are commercially available. There have also been interesting trials to make very, very long columns, but in case of very long columns, the efficiency starts decreasing again. So it has been found that for a pretty standard sample, roughly a 30-meter column is quite good choice as a first option. Another important parameter in the capillary columns is how thick is the stationary phase that is actually covering the inner wall of the capillary column. And there are two competing processes. Firstly, when the layer becomes too thick, then the diffusion in the stationary phase becomes too slow. So in the van Deventer equation, our C term, which is how efficient is the diffusion of the analyte to the stationary mobile phase border, becomes too inefficient, and therefore peaks become broad. So we don't want to have a too thick layer on the walls of the column. However, when we make it too thin, then the columns are not able to take up too large quantities of the sample. So the capacity becomes very low, which means that we can inject only very small sample quantities and only very low concentration samples. So this is also something that we don't really want. And therefore, kind of a standard is to have a 0.25 micrometer thickness of the stationary phase on the inner wall of the column. However, in some cases where we need to improve the capacity, for example, we have very volatile compounds, or we need to inject very larger sample quantities, then we can also have larger thicknesses of the stationary phase on the column. And the capillary columns are very good because they are very efficient in separation of complex samples due to their ability to keep the peaks very narrow and keep the efficiency very high. And from the efficiency point of view, the theoretical plate numbers of 100,000 or above are completely normal to be achieved with out of the box capillary columns. Now, let's dig into the stationary phase that is then causing the retention of the compounds. Important part of the interaction between the analyte and the stationary phase is the polarity. So let's revise what kind of interactions we may actually have between the analyte and the stationary phase. To remind, when we talk about polarity, then in case of pure liquids, we would mean the dipole moment of this liquid. So this is when we just have one liquid in a beaker or in a flask, and we would think, oh, how polar this liquid is. Then we would look up what is the dipole moment of these molecules, and we would be able to say, okay, this solution is, this liquid is more polar than the other liquid. And this dipole moment directly influences also the boiling point. So the higher is the dipole moment, the higher is also the boiling point. More polar molecules are having higher boiling points. But in here, in gas chromatography, with polarity, we are actually meaning something which is, it is a combination of the polarity of the solute, so our analyte, and the polarity of the stationary phase. So we are thinking about the interactions of the analyte and the stationary phase. And broadly said, we have van der Waals forces that are causing these interactions, and we have hydrogen bonding. Both of these contribute to the interactions. And from the van der Waals forces, we have also three different types of interactions that we can have. We can have disperse or London forces, which are induced dipole interactions. And these are occurring for all compounds independent of any, of the presence of any polar bonds in these molecules, so any dipoles. And this means that if we have a stationary phase and if we have a solute that don't have any dipoles, this is still present, and this is causing the compounds to be retained still. And this is also very nicely correlated with the boiling point of the compounds. Now, if one of the compounds, either the stationary phase or the solute, has dipoles, so there are some polar bonds that cause a dipole, then we can also have induced dipole interactions. And this now is something that comes in addition to the boiling point. So this means that if the induced dipole interactions can be present, it might not be purely the boiling point that is determining the elution order of the analytes. And if both the analyte and the stationary phase have some polar bonds, so we can have dipole-dipole interactions, then these can also additionally increase the interactions between the analytes and stationary phase and cause the polar compounds to retain stronger than could be just decided based on the boiling point. However, we have to keep in mind that the boiling point is also actually capturing the dipole-dipole interactions between the analyte molecules. So if we have any kind of polar interactions, the boiling point is a rough guide, but almost never we don't see exactly boiling point increasing retention times unless we have homologue series. So if we have homologue series where the functionality is exactly the same, the polar functionalities are exactly the same from analyte to analyte, the only change is the alkyl chain length, then we see extremely nice correlation between the retention times and the boiling points of these compounds, because the only thing that is changing is then the dispersion forces between the alkyl chain of the homologue series analyte molecules and the stationary phases. In addition to the van der Waals forces, there can also be hydrogen bonding playing role, and this is especially true for the polar stationary phases that we will have a look at. And or actually the most polar stationary phases. And the problem of hydrogen bonding compounds can also occur. So sometimes the compounds that can give hydrogen bonds are tailing on the chromatograms, and this can be caused by the unwanted adsorption to the stationary phase or to the slightly exposed capillary walls or to the liner in the injection system, and therefore functionalization of possible silanol groups. So mostly the other part of the hydrogen bonding that the analytes giving the hydrogen bond with is a silanol group, either then on the glass, in the glass liner in the injector, or on the in the column material, on the silica material. So these silanol groups can be functionalized to make them more inert and avoid this tailing for the more polar compounds. So now we actually have the stationary phases, which are of very different polarity. So there are some which are arbitrarily said to be polar, and some which are said to be very non-polar. And the polarity of them is the polarity range between these two ends can be measured and compared, and there are tables where you can look up which stationary phase is how polar compared to another stationary phase. However, it is still sometimes not only possible to look at the tables with these different polarities, but also to actually try out because of specific interactions that can occur between specific compounds with functionalities. However, there are some general guidelines that all stationary phases should be fulfilling to be usable in the gas chromatography. So most of the stationary phases today are liquids, and this is also why a kind of term gas liquid chromatography can be used or has been used to denote that actually the stationary phase is liquid. This was a especially useful term at the times where also really solid particles were also used as the stationary phase in the packed columns. The liquids, however, need to be low vapor pressure liquids, which means that they would not themselves vaporize and escape the column. So we would need them to be very stable in the column and not to come out from the column. And they would also need to be thermally stable. So different stationary phases have different temperature limits, and it is very important that the temperature limit would be much above the column temperature that we actually want to use to carry out our chromatography. And the low vapor pressure and thermal stability is also important to reduce something which is called column bleed. And column bleed is the stationary phase in time escaping from the column. So just being kind of washed out from the column and making the stationary phase constantly thinner in the column, and also causing background in the detectors very often when we are using generic detectors that are able to detect very many compounds. So we want to keep this bleed, so this leaving of the stationary phase from the column, as minimal as possible. So therefore, the stationary phase, the liquid as a stationary phase, should be low volatility, and it should be also temperature stable. It's also good when it has a low viscosity, so that the mass transfer would be as fast as possible, so that we wouldn't cause any additional peak broadening. And it's also important that it would interact with the analyte, so either due to the dispersive interactions or due to the dipole-induced dipole or dipole-dipole interactions. kind of classical stationary phase with the least polarity is squalene. This is a high molecular weight alkene with a somewhat branch chain, and this is termed as the least polar stationary phase. And in the stationary phase tables where the polarities have to compare the polarities of the stationary phases, this is kind of the zero reference point with the lowest possible polarity. And this comes from the fact that there are no functional groups that could give any other interactions than the induced dipole interactions. The problem with squalene, however, is that it has a very low upper usage limit. So this is only 125 degrees in Celsius, which means that if we want to increase the temperatures, then this is highly problematic. And therefore, this is now not very much used. And actually, silicon polymers, so polysiloxanes, are highly used. The least polar polysiloxane, which is called also OV1, is a polysiloxane which has methyl groups attached here. So methyl groups are also able to give induced dipole-induced dipole interactions, and the least polar is the column where only methyl groups are attached to the polysiloxane. Now, in order to increase the polarity of the polysiloxane stationary phases, also phenyl groups or cyano groups can be attached instead of the methyl groups. And the phenylation percentage can be somewhere between 5%, which is still relatively least polar stationary phase, to about 50%, which is then a medium polarity stationary phase. But in the silicon polymer stationary phases, it's a fairly polar stationary phase. And phenyl groups are making the stationary more polar because they are the induced dipoles are stronger in the benzene rings than they are for the methyl groups. So if our analyte molecules are having dipoles, so they have polar groups, then the induced dipole-dipole interactions are stronger with the phenyl groups than they are with the methyl groups. And therefore, even though we aren't introducing ourselves to this stationary phases any polar bonds, they are acting as more polar stationary phases due to the fact that the induced dipole-dipole interactions are stronger with the phenyl groups than they are with the methyl groups. Because these are polymers, they are also more stable to the temperature, and the stability can be up to 350 degrees or maybe even 375 degrees. So this is the temperature that can be used to chromatograph, which is a fair temperature range. And most of this chromatographic separations are done in this region. However, sometimes there is a need to have even higher polarity to obtain even better selectivity. And for these cases, the most polar stationary phase is a Carbowax, or Carbowax 200M, 220M, sorry. 20M refers to the molar mass of the Carbowax. And Carbowax is essentially a polyethylene glycol, which is polymerized and then used to cover the inner wall of the capillary column. It is a bit less stable than the silicon-based polymers, so up to 250 degrees, but it gives additional selectivity due to its additional polar interaction. So here we actually have this CO bond, which is polar, and also the oxygen is able to give hydrogen bonds. So this gives additional selectivity here compared to the methylated silicon polymers. So let us look what kind of selectivity changes can the stationary phase cause. So here are two chromatograms of the same compounds. So the heptane, tetrahydrofuran, two um, two butanol, as well as N-propanol, and they have boiling points in the range of 64 degrees to 98 degrees in Celsius. And these compounds have been chromatographed with polar stationary phase here above, and with a less polar stationary phase here. So the upper one is with the carbovax, so the most polar stationary phase. And we see that even though heptane has a very high boiling point in this among these compounds, it actually elutes as the first one from the polar column. And this is understandable, as this compound, heptane, doesn't really give any polar interactions with the stationary phase. However, propanol, which also gives hydrogen bonding, is the last eluting compound. And now, interestingly, we can here also compare the elution order of the compounds from the polar stationary phase to the non-polar stationary phase. And we can see that actually here the order of the compounds elution is completely reversed. And we also see that even for the non-polar stationary phase, it is not directly linear to the boiling points of the compound. So the retention is affected by the boiling point of the compounds, but it's not a straightforward correlation. Now, in order to actually carry out the chromatography with the gas chromatograph, we need to achieve conditions where all of the compounds that we are interested in, and that are, or actually all of the compounds in our sample, would be able to pass through the column, and at the same time should also be separated. So we would need the column temperature to be sufficiently high that all of the compounds actually pass through the column. So meaning that they would not only be stuck in the stationary phase, but they would actually partition between the stationary phase and the mobile phase, and would actually slowly pass through this, through our column. At the same time, what we also don't want is that all of our compounds would be in the gas phase. So we don't want that the column temperature is so high that the compounds are all in the mobile phase, or at least many of them would be all completely in the mobile phase. Because what happens then is that then they are just in the mobile phase and they all pass the column very, very fast. So we wouldn't get any separation of the compounds here either. Usually, we can achieve this by having a column temperature that is much lower than the boiling point of the sample. And this is indeed due to the fact that we need to have our compounds partitioning between the stationary phase and the mobile phase. We don't want them to be completely either in the mobile phase or in the stationary phase. If the temperature is too high, they are always in the mobile phase. If it's too low, then they are stuck in the stationary phase and don't move through the column at all. And finding this temperature is the critical part in the separation of the compounds in the gas chromatography, and can be very, very challenging. So let's look at an example of a chromatography of N-paraffins, which are a homologous series. And here above, on the above chromatogram, these compounds have been chromatographed at 150 degrees Celsius. And what we can see is that the lower paraffins with the shorter chain length, they are all kind of close here together, and some of them aren't even really separated. While after 95 minutes, which is more than 1.5 hours, the largest paraffin that has eluted from the column is C15. So we could easily think that this is the last paraffin. So we could stop here chromatographing and saying, okay, that was it. But actually, there were also other longer chain paraffins here. Um, and what we also see as a problem here on the upper chromatogram is that the peaks become broader as they elute later. So the peak that elutes, the C15 peak that elutes here at 19 minutes is almost 5 minutes broad, while the peaks that eluted here in the very beginning were like minute or less broad. So this chromatography system where we use one temperature and we call this an isothermal run is not really very sufficient for this kind of a sample where the boiling points of the compounds range in a very, very wide range. And to solve this, there has been created something which is called a temperature program. And this is the case where we rise gradually the temperature of the column as we chromatograph. So we start by one fixed temperature and then we increase the temperature. And for an example of the power of this temperature program, we can see here from the same paraffin separation, the initial temperature was 50 degrees and it was rose to 250 degrees by 8 degrees in a minute. So we can see here two things. Firstly, because we started with a lower temperature than was used here in the isothermal separation, the first peaks are also nicely separated. We see C6 separated from C7 because the boiling point for both of them is higher than the initial 50 degrees that was used as a very first starting point of this temperature program. And we see a nice separation of all of these compounds, but what we also see is that there are actually many more compounds than we saw in the isothermal separation. We can see here also C20 and C21. And in spite of the fact that they have longer retention times, they are not necessarily broader peaks. So we get a significantly better signal to noise ratio and therefore also the LOD for the C19, for example, in here. So we see that the peak is much, much narrower and much sharper, and the peak is much better to separate from the baseline in case of this temperature program chromatography. So therefore, we see that with the temperature program, which is increasing the temperature of the column gradually during the chromatographic run, we avoid peak broadening with the longer retention times. We also get the analysis done much faster. So we see that here the last peak is eluting at 36 minutes, while here it was much more than 95, because at 95 we only got C19 eluting from the column, and C21 we didn't see at all with this time. As well as because the peaks are get narrower, we get better signal to noise ratios and therefore lower LOD values. So temperature programs have significant advantages for the chromatographing of samples where the boiling points of the analytes have a wide range. Temperature programs are therefore ideal for screening of the sample when we don't know generally how many peaks we are expecting or what kind of retention times we are generally expecting to have for our samples. So therefore, in these situations, temperature programs are ideal. And temperature programs, though very vastly applied, even if the final aim is to get an isotemperature isothermal separation in the end, doing a first screening with a temperature program is very good to get a good overview of the sample and at what times, what temperatures the compounds are eluting from the column. It's also very good because column cleaning is kind of built in. The problem can be with isothermal separation that matrix components, which have low volatility, are not eluted from the column with the isothermal separation, and therefore can kind of build up in the column and cause column properties to change or to increase baseline. So for temperature programs, because the temperature goes up in the during the temperature program, these high low volatility matrix components are also more likely to get cleaned out from the columns. So this is good for preserving the columns and keeping the baselines low. So the kind of technical detail is that the injector, the column, and the detector need to be here thermostated separately, because the column temperatures start from very low temperatures, while the injectors used to be need to be quite high temperatures. So this is a technical need to have them separately controlled. And it's also important that when we use temperature programs, the liquid phase that we use as a stationary phase would be stable over the whole temperature range that we use for the chromatographic analysis, as well as that it has sufficiently low viscosity also at the lower temperatures where we start our chromatography. So this means that the earlier peaks would not have somewhat less efficiency due to the slowed down mass transfer in the stationary phase. So this is also important. Now, when we have our compounds separated and carried out from the column, we also need to detect them somehow to see what columns were there and also to quantify them. And some of the most common detectors in gas chromatography are the flame ionization detector and also mass spectrometry. But traditionally also electron capture detector is popular, but there are many, many other detectors. And just to give you a short kind of link, there are also thermal conductivity detector, which is kind of, let's say, least selective detector. Also nitrogen phosphorus detector to specifically detect compounds containing nitrogen or phosphorus, as well as for obtaining somewhat more structural information, coupling of GC with infrared spectroscopy is possible. Let's look at some of the most popular detectors one by one. So the kind of golden standard in gas chromatography is the flame ionization detector. The idea of the flame ionization detector is that the effluent from the column is mixed with a hydrogen, which is later mixed with an air. And this mixture is lit in fire so that the hydrogen is burning in as a mixture with the air. So we have a flame here. And in these flames, ions are produced from compounds that contain carbon. So carbon-containing compounds somewhat pyrrolize in this flame and produce cations, which cause conductivity in this flame. And to measure this conductivity, there is a collector electrode just on top of the burner of the flame, and we measure the conductivity as from the collector electrode relative to the burner tip. So the conductivity is measured between these two electrodes. The collector electrode up on top of the flame, and then the tip from the flame carrier. Now, because the compounds that cause the conductivity are compounds which were kind of pyrrolized in this oxygen hydrogen flame, they have to contain carbon. So all compounds that contain carbon almost are giving a signal in the flame ionization detector. And this is also the sole source why it is so widely used and why it's kind of a golden standard for gas chromatography analysis. Generally, the response is proportional to the number of carbon atoms. So ethane has twice larger signal or response factor in flame ionization detector than does methane. But heteroatoms such as oxygen and nitrogen decrease this signal. So, for example, CO2 does not give any signal in the flame ionization detector. But this is kind of an exception. Also, for example, ammonia, which contains only nitrogen and hydrogen, doesn't give any signal in the flame ionization detector. The same, for example, for water. But compounds that do contain carbon-carbon and carbon-hydrogen bonds. They do give signal, and roughly said is proportional to the number of carbon atoms, but oxygen and nitrogen bonds with carbon decrease this response. This means that in order to do quantitative analysis, to get good quantitation, we need actually analytical standards to construct the calibration graphs and to quantify the compounds, because the response is not directly proportional to the carbon number. There are small variations. Generally, the detector temperature should be sufficiently high so that the compounds that elute from the column would not kind of precipitate or condense in the detectors. In case of flame ionization detector, it's also additionally important that the water that is being formed during the burning in the flame would not condense. So it has to be at least 125 degrees, but usually it is somewhere above 250 degrees. It is very sensitive, so the LOD values to BPB level can be achieved. Of course, compounds which have more carbons, they are more, for these, the flame ionization detector is more sensitive. It also has a very wide linear range up to 6 orders of magnitude, which is ideal for quantification purposes. It's also very robust and stable, so there aren't much of a variations if all the flow rates of the gases are kept constant and closely reproducible flows of the gases are achieved. And it is suitable for almost any organic compound that contains carbon-carbon-carbon hydrogen bonds. And also all carrier gases are possible, so nitrogen and helium, of course, but also hydrogen can be used, though, as said before, hydrogen is not really suggested due to its dangerous properties. And now, some compounds also contain other atoms that could give advantageous detection properties. For example, classically pesticides contained a lot of halogenated halogen molecules, and halogen molecules have actually another advantageous property for detection, and this has been used in the electron capture detector to get especially low detection limits for compounds containing halogens. Namely, the halogen atoms are able to capture electrons, so attach electrons from the gas during collisions with the electrons, essentially. And what happens in the electron capture detector is that we have a radioactive source, so nickel-63, which is a source of beta particles, and these beta particles can then react with the nitrogen which is used as a carrier gas, and during the collision, electrons are emitted from the nitrogen. So therefore, we have here in this part electron-rich medium, and when our analyte molecules are coming with the carrier gas to this detector, then they capture the electrons, and with this they reduce the conductivity in this medium, and this conductivity is measured by measuring the conductivity between the cathode and the anode here. So analytes decrease the conductivity, and here any compound that is able to capture the electrons can be detected. And this means largest sensitivity for the halogenated atom containing compounds. The drawback of the electron capture detector is the radioactive source that is used here. And it is also not so robust. So any kind of contamination can build up here and cause instability from day to day, from sample to sample. However, if we are having analytes which contain halogen atoms, then extremely low detection limits can be achieved, even 10 times, even lower than with flame ionization detector are possible. And it also depends on how many halogens are present in the molecule. So the higher the number of halogen atoms, the more sensitive analysis can be performed for these compounds. The linearity is usually lower than for a flame ionization detector, so around 3 orders of magnitude. And also the sensitivity depends on which of the halogen molecules atoms is present in the molecule. So iodine, Jobert's iodine, the sensitivity is the best and lowest for the fluoride. The stability of the electron capture detector is not as good as it is for the flame ionization detector, so contamination is a big problem. And it's very important that the nitrogen that is used as a carrier gas is ultra pure to get nice, stable conductivity. Lastly, you will actually have a specific lecture about mass spectrometry later, but mass spectrometry is also a very important detector in both gas chromatography and liquid chromatography, and it was first used also, of course, for gas chromatography. And usually we use something which is called electron ionization mass spectrometry, which is able to detect almost all compounds. But the limits of detection highly depend on the compound, and it is compatible or compatible with detection limits in the flame ionization detector. So it is in the ppb range, or for some compounds it can even be in the ppt range. The linear range is somewhere between the linear ranges of the electron capture detector and the flame ionization detector, and the sensitivity is increased for compounds which have polarizable functional groups. So aromatic compounds or some polar functional groups such as chlorine or ammonium group, they all improve the sensitivity of the mass spectrometric analysis. However, the largest advantage of mass spectrometry as a detector in gas chromatography is that it is kind of selective in the sense that we not only register the retention time of the compound and the peak area, but we also obtain mass spectra of the compounds, which allows us to at least tentatively identify the compounds or get some additional clues what compounds they could be, even if we don't maybe have the analytical standards in the lab, or we aren't directly aiming to analyze, aiming to quantify specific compounds. We can also look at the other compounds that have been present in our sample. So for example, if the peppermint oil characterization is done, then we could look at each of the peaks and see what is the mass spectra behind this peak, and then use the spectra to identify the compounds. And it's not only that the spectra as such can be analyzed by the analyst, but there are also nice libraries available for the gas chromatography mass spec analysis. For example, one very famous one is the NIST library, which is almost built into all of the GC-MS analysis. And this is very convenient to get some clues what compounds were present in the sample when you also want to look at other compounds than the ones for which you have analytical standards already there. So now to kind of sum it up, but also give you perspective into the limitations, the analytes that we are determining, as said many times until now, they have to be volatile. So generally, we can predict which ones of them can be analyzed based on the boiling points. We can also generally say which of the compounds would elute earlier and which would elute later based on these boiling points. And they also need to be stable. So the compound should not degrade at the temperatures that we need to use for the chromatographic analysis. And the same is valid also for the solvent that we use and solvent additives. So we should actually use as pure solvent as possible so that there would be as little impurities as possible. The impurities of the solvent cause us coast peaks, so peaks that don't actually belong to our sample. So the solvent purity is also very important. Now let's look how the boiling point of the compound determines on is associated with the structure of the compound. Firstly, let's look at the row here. So we have here from C4 to C8 to C12. And we see that if butane is actually a gas at room temperature, its boiling point is -1 degrees in Celsius. Then the C8 octane is already having a boiling point of 126 degrees. And dodecan, so C12, has even the boiling point of 216. Still, all of these alkanes from C4 to C12 can be determined with the gas chromatography. So the temperature range of their boiling points is sufficiently, the temperatures are not too high. However, here temperature program would of course be useful to actually get a good separation of all of these three alkanes, or maybe also the alkanes that have not been indicated here, but which are with an intermediate number of carbon atoms in between them. However, when we start adding polarity, so for example, when we look at the monocarboxylic acid of C8, then we see that even though we didn't add any carbon atoms, but we did have add carboxylic acid group here, the boiling point rose dramatically. So we have a boiling point more than 100 degrees in Celsius higher. And if we actually look at the C8 dicarboxylic acid, then here the temperature has rose dramatically to even more than 450 degrees. And these temperatures are too high to be actually chromatographed nicely. So for example, the analysis of such very polar molecules or molecules with very polar groups, such as the dicarboxylic acid here, is directly impossible with the gas chromatography due to the temperature limitations. However, to overcome this, derivatization is very widely used in gas chromatography. And this derivatization is the reaction of the analyte to change its properties so that it would be possible to be analyzed with a gas chromatography. And for the carboxylic acids, this reaction is very often esterification. So for example, methylation of the carboxylic acid groups to the corresponding methyl esters. And we can see that here, if we would methylate these carboxylic acids, we would be able to decrease the boiling point of the monocarboxylic acid by about 40 degrees. But the effect is even larger for the diacid, where we can actually now reduce the temperature to 268 degrees, so that this compound now becomes also analyzable with gas chromatography. So therefore, for example, fatty acid analysis, derivatization via esterification is a very common tool to enable gas chromatography analysis. We don't do only quantitative analysis with gas chromatography. We largely, or maybe today even mostly, do also quantitative analysis. And quantitative analysis exclusively is done in gas chromatography with a calibration graph method due to the fact that response factors with any of the common detectors are not the same for all of the compounds, and they are also not directly obtainable from the structure of the compounds. So therefore, calibration graph method is the most advantageous way to quantify the compounds. Additionally, due to the fact that injection as well as the split can be somewhat not so good reproducibility, internal standard method is advantageous in the gas chromatography quantification. And these small variations in the injected sample volumes can very nicely be accounted for with internal standards that have been spiked into the samples. So with this, the gas chromatography analysis can also very nicely be made quantitative. So this was an introduction to the gas chromatography, which is then primarily for the analysis of volatile organic compounds or compounds that can be turned volatile with the derivatization. In the next lecture, we'll also look at how even more polar compounds can be analyzed with the liquid chromatography. Good luck.